Hello there, environmental engineers. Today we're going to look at primary clarification. So we've got a relatively simple introductory problem from the textbook. Now we have the influent coming in to two separate clarifiers. And so this is an example of a question where you see it in words and it's not immediately clear what this looks like in practice, especially if you've never been to a wastewater treatment plant. And so let's start with the clarifiers. The clarifiers are cylindrically shaped, and they're much wider than they are tall. I drew it a little bit out of proportion here. And you have water that comes in from the bottom and very slowly flows up. And the goal is so that it flows up so slowly that the particles that are in it settle down faster than the water is flowing up. And so you get cleaner water that's floating up to the top, flowing up to the top, I should say, and sludge, which forms at the bottom and is removed at the bottom. Now, the cleaner water up at the top, it slowly overflows over the lip, over something called a weir at the lip. And that happens evenly all around the perimeter of the clarifier, and it's collected there and channeled off to the next process, which is probably activated sludge. So let's get started on this. We've got an inflow of 5 mgds. Now that's million gallons or megagallons per day. I write it like this. And the only other numbers we're given are the radius and the depth of our clarifiers. So part A, what is the detention time in each clarifier? So the detention time, we often write that as theta. That's simply equal to volume over flow. And so this will give us a unit of time. The detention time is it's a measure of how long the average water particle spends inside the system. So that could, depending on the size, that could be from seconds to days. You can measure this for the Great Lakes and it can be years. So the volume, this is just the volume of a cylinder. Volume equals pi r squared times d. Clean that up a bit. Pi r squared times d, which will be pi times 43.0 feet squared times 10.0 feet. Now, I'm not going to solve this equation just now. I'm going to leave it like this, and I'm going to plug it all into the final equation to solve it all at once, so that there's only one calculator step. I find that makes me less prone to errors. And then Q, well, that's going to be half of the influent flow. Why half? Well, you're in engineering school. I think you know why. So 1/2 of Qn equals 2.5 times 10 to the 6 gallons per day. So each clarifier will get 2.5. 2.5 here and 2.5 here. We're splitting at this point, and we get half the flow in each clarifier. So now theta equals V over Q equals pi times 43.0 feet squared times 10.0 feet. We put that over. We'll put that over Q, which is 2.5 times 10 to the 6 gallons per day. So we have days here. That, because this is on the bottom, it's on the denominator of a denominator, that'll flip up and that'll be on top. We'll have our units of time. But we're not going to be able to cancel out our other units. So we have feet squared times feet, that's cubic feet on top, and gallons on the bottom. So we're going to need a conversion factor here. Let's put it on the top. That'll work it just a little easier. So we have 7.481 gallons in 1 cubic foot. And if you need that on the exam, if your professor is at all reasonable, you'll have that number, that conversion factor given to you. It's not normal to have to memorize these things. So we work this all out, plug it into the calculator, and we get 0.174 days. Now, it doesn't give us specific units in the problem, but we can see that the other parts of the problem are in hours, use units of hours rather than days for time. So I'm going to convert it to hours. You don't necessarily need to do this. So we have 24 hours in one day. Days will cancel out. And that gives us 4.17 hours. That's our detention time. Part A is done. So part B, we're asked for the hydraulic loading rate. Now, I've usually heard that called the surface overflow rate. And what this comes down to is the speed at which water is moving up. Because remember, we have water moving up in the clarifiers very slowly so that the particles will fall down faster than the water's flowing up. They won't get carried up in the flow. And so they give us units of feet cubed per feet squared per hour. Now, this simplifies to feet per hour. That's length per time. It's like meters per second or kilometers per hour. This is a speed. That's the easiest way I find to think about it. And the surface overflow rate, that's just Q over A. So we know Q. Let's find A. A is pi r squared. It's pi times 43.0 feet squared. And let's plug that into the final equation like that. We have 2.5 times 10 to the 6 gallons per day over pi times 43.0 feet squared. And remember that we wanted the units of feet cubed per feet squared per hour. Now, we're going to need to replace the gallons with cubic feet and replace the days with hours. So might as well do that now. So we've got 1 cubic foot per 7.481 gallons. And we have 1 day per 24 hours. So our days cancel out, our gallons cancel out. We're left with feet cubed per feet squared per hour. Plug that into the calculator, and we get 2.40 cubic feet per square foot per hour, or equivalently, you can call that 2.40 feet per hour. I like to write it that way. It reminds me that this is a speed that we're talking about. Part C, what is the Weir loading rate? Now, I usually hear this called the Weir overflow rate. So I write the abbreviation WOR. Weir overflow rate, that's just Q over C, the circumference. Now, the reason this is important, so remember that the cleaner water, the settled primary wastewater, is flowing over the edge all around the perimeter uniformly. And we've got that weir running along the edge. Now the weir just looks like a sawtooth shape along the edge. But the reason the weir overflow rate is important is because if we're flowing water over the weir at too high a rate or too quickly, that will create turbulence. Now, imagine trying to settle sediment out of wastewater when there's turbulence. It's just not going to work. So, in any design, you have appropriate bounds for your weir overflow rate. So, circumference equals 2 pi r, or pi d. So that's 2 pi times 43.0 feet. And the Weir overflow rate is 2.5 times 10 to the 6 gallons per day over 2 pi times 43.0 feet. Now here we wanted units of feet cubed per foot per hour. So again, we're going to need to do some conversions. We can do 1 cubic foot is 7.481 gallons. And 1 day is 24 hours. Plug that into your calculator, and it works out to 51.5 cubic feet per foot per hour. So there you have it. I hope that answered your questions. If there's anything that's unclear, or if you have a follow-up question, feel free to mention it in the comments. And, well, if exams are coming up and it's feeling like crunch time, you're a little bit lost, I am a tutor. I'm here to help. Don't hesitate to get in touch. I'll see the details in a moment.